Sorry, guys. Hello. I know that some of you are waiting probably on the other one. Let me just quickly fix that one. Just give me a second. I had a technical error which I didn't have in any of the other dice. So I'm just going to quickly fix it right now. Right. Sorry, guys. I'm still trying to quickly fix this one. I'm just getting a new link. Just give me a second. Hello. Hi. Can you hear me, everybody? I'm really sorry. The link that I made earlier is not working for some reason. I sent the link for the correct one on the other one, so I could possibly see, but there were a lot more people waiting on the other one. Let me see. Let me send that link again to everyone. So it looks like the previous streaming link I have made in a slightly different way. Okay, so right. In the meantime, while others join, can you please, while others join, can you please let me know whether you are doing combined science or triple C or T? This is mainly for higher tier viral vibes, but it can work for foundation because there are a lot of overlap as well. Thank you, Ishal. Yes, I know you're triple. Ishal, triple higher tier. Triple science higher tier. Thank you, thank you. Yeah, getting a lot of people, guys. Let's see if there are any more people waiting on the other one. Let me just send the link a couple of times just in case people are confused with this one. There are still 43 waiting on the other one. Hopefully they will find their way to this one. I'm just going to quickly mute this for a second. Sorry, guys, I had a technical difficulty just at the beginning of this thing. I can still see there are 43 people waiting on the wrong one. So I'm just sending the correct one to everyone just in case. Hello, Grace. Okay, good to see you, Mukesh. I see a lot of familiar names from your maths revision sessions and all that. Okay. We'll get started. Right. I don't know. Maybe when I said it initially, something must have gone wrong. Right. Okay. We're getting started now. So I've looked into the previous papers, and I also I know what are the common things that you normally get. Can everybody see my screen, and can everybody hear me well? Hello? Right. Now, these are some of the very common things that you get in your exams. The ones that are in a white background are just the normal combined science content, and everything is relevant for those who are doing triple. So if you are triple, you need everything. If you are doing combined sciences or you're doing foundation combined science, you will need mostly the ones that are in these white boxes. So the way we are working today is I'm just going to quickly explain some of these theory parts here, just like a really quick recap, really. And then we are going to do more exam question based approach, right? Okay, I can see a lot of my students there. Vishal, Ayub, Jude, I can see there. Okay, good, good, good. And I can also see some of the familiar names that I've seen in the paper one and all that, right? Previous maths things and all that, right? So tomorrow is your last science paper, right? And some of you are just for some of you, I just heard earlier when I was doing some lessons, people said that is their final paper tomorrow, or some of you have one more paper or something. So great. So just give it a proper question, this last one, and I will help you for this. Yeah. Now let's just quickly look into these things. So I'm just going to take some of these things one by one, and we're going to discuss a little bit, and then discuss about the other things. Now let's have a look at the formulae. So these are the stuff that you guys need. So let's see what formulae you need to know. Now, initially when I made this image, I had this this filled up, but then I thought I'd rather do it like with you guys. I'm sorry, it's just taking a second to open this up. I don't know why. Yeah, there you go. So I thought it's a good idea if I just quickly explain it and write the formula as we are here. So the formula for weight here is W is equal to mg. They see if it says recall, that means you guys need to know it. Work done is given by the formula F times D. For F is the force, D is the distance. Hooke's law, the formula is F is equal to Kx, where K is the spring constant and X is the extension. Elastic potential energy, there are two versions here, guys. Half Fx, also half Kx squared. You guys can take a screenshot at the end when I've completed this, right? Good, good, good. I can see the topics coming up in the chat and all that. That's really good. Now, Newton's second law, the formula is F is equal to ma. Speed is equal to distance over time. For velocity, we have displacement over time. I'll just add velocity here. Good, good, good. Some of them will be given, some of them, if it says recall, you don't, Mukesh, you will not be given them. Some are given, some are not, okay? So you need to know all of them. Plus, if you don't know the formula, where it comes from, that means you don't know your theory part well enough. So it's good to know them. V squared minus U squared is equal to 2A. Yes, thank you. Yeah. Yes, yeah. Some of them are given, some are not given, right? So I can see that you're saying some of your yes, some are given, some are not. So you need to know, yeah? Good. Momentum, P is equal to mv. Wave speed, V is equal to F lambda. Wave period, periodic time is 1 over frequency. Force on a conductor, right? Just don't bother about the last one, okay? These are the main formulae, guys, right? These are the combined science ones that you need to know, right? We can do the magnetic field one as well. Let me just add this one. F is equal to BIL. So F is the force, B magnetic field strength, I current, L length. So when I save it, you guys can take a screenshot so that you know exactly what you guys need for that. All right. So that's the combined ones. And now quickly, yes, B is the magnetic flux density I saw. Yes, that is the one. I'll quickly write the triple ones as well here, but this will only apply to those who are doing triple. Others, just it's only going to take like a minute, so just don't worry about this one. So the moment of a force is given by the formula m is F times perpendicular distance. Principle of moments says the sum of clockwise moments is equal to the sum of anticlockwise moments, right? Pressure is force over area. Pressure in liquid is H rho G. H is the depth, rho is the density, G is the gravitational field strength. Change in momentum, this is a hard one. F is equal to mv minus mu over t. We will discuss this in the triple part at the end. Transformer turns ratio, N primary divided by N secondary is equal to V primary divided by V secondary. Transformer power, VPIP is equal to VSIS. That's it, guys, right? If you are combined, please don't worry about this bit. If you are triple, please take a screenshot. So all of your questions, right, are based on what we just discussed here. Now, let's have a look at some of these theory parts here, guys. Right? We are now going to quickly do some questions. Now, I'll tell you what we are going to do. So I showed you the most common questions that you normally get, right, which are on these things. You can take a screenshot of this. And I'm just going to quickly show you some of the theory parts really quickly on one part, and then we'll do some questions. A quick theory and then some questions. So please let me know in the chat if you want to do anything in particular. Like, if you want help on anything in particular, do let me know. Right? Right. So you need to know how to differentiate between vectors and scalars. Remember, scalar quantities have only magnitude, and vector quantities have both magnitude and direction. Scalar quantities are like speed. Vector quantities are like velocity. Then acceleration, momentum, all that. Distance is a scalar. Mass is a scalar. Weight is a vector, all that. Contact and non-contact forces. Now, contact forces are when if the two objects needs to be very closely associated, right? Thank you, Weber. Yeah, bears fun. Yes, all of them are correct, right? For example, imagine if you keep an object on a table. Now, the object pushes the table down. The table pushes the object up. This is what we call the reaction. Yeah. I'm going to mode and generate effect. Yes, microphone, loudspeakers. Yes, happy days. I'll be doing that. Yeah. I will explain them. Then what we are going to do, guys, if you want a quick glimpse of like what we're going to do, we are going to do all of these exam questions as well, right? But I'm just going to quickly show you some of these things just to show you, right? Non-contact forces are, imagine you have a positively and negatively charged objects. They attract, but they act at a distance. If you have a north pole and a south pole, they attract at a distance. These are non-contact. Weight and mass are connected by the formula W equals mg. Resultant force is the overall force on an object. So if you have an object and say you go 20 newtons to the right and 8 newtons to the left, the resultant force is obviously 12 newtons to the right, like that. So work done is equal to force times distance. So if you exert a force, guys, remember, if you're doing triple, the moment formula is also FD. People are like, okay, are they the same? No, they are not. Because here, work done is force multiplied by distance moved in the direction of the force. In the moments, it is force multiplied by the perpendicular distance. Right? If you're triple, you will need to know the difference between the two. If you are combined, you don't really get the second one, so just don't worry about that one. Then Hooke's law, F is equal to Kx. We will do a question on that. Right, guys, that was a really quick recap on this part. Now, we're just going to do a question here. So this is what we are going to do. I'm going to give you some questions and I'm going to run a timer so you guys can try the question yourself and then we can discuss these things, right? And please send me the answers in the chat. Yeah, do it. Send me the answers in the chat so I can see what answers you got, right? Great. So let me just quick the timer up actually. Give me a second. You guys can start the question now. You can start the question now. I'm just getting my timer somewhere here. Just do the question, guys, and we will discuss this in a bit, in about a minute. If anybody came just now, guys, we are working on this AQA specific physics questions. In the first 1 hour, 1 hour 15-ish, we are working on combined science content. And towards the end of the session, I'm working on triple science content. Yeah. So what we are doing is we are discussing quick theory parts and then exam questions. Yeah, like this one here. This is the first question. We will discuss this in about 30 seconds now. Right, okay, sorry. Now I got my timer, so that's all good. Right, guys, let's quickly discuss this one now. A skydiver of mass 75 kilogram jumps from a plane. Okay. Calculate the weight of the skydiver. So obviously W is equal to mg and the skydiver's mass is 75, g is 10, 75 times 10, 750 newtons is your answer. Now, in your GCSEs, you're okay to use g as 10. Most questions say to take g as 10. If a particular, sometimes if you use the more accurate value of g, that's perfectly fine. I think a lot of you know what the value is. Send me in the chat what the value is. What we call approximately 10. What is the real value, guys? What is the exact value? 9.8. Thank you, Aisa. Right, it is 9.8, 9.81 to be more precise. But plus, guys, another thing, it actually changes little by little. Right? I mean, on different places of the Earth, it's not the same. And if you go away from the Earth, it's not the same. There are some slight differences in this, but we don't really consider that. On average, it's 9.8, but GCSE 10 is fine. But I've seen like some people more using 9.8 as the instead of 10, right? So physics is the subject that I mark as an examiner. So although I teach other sciences and maths as well. So I've seen this multiple times, guys, but usually mark schemes allow for it. But Why would you go with 9.8 when the question clearly says 10? That's really not useful or even not necessary. 750 is something you can do on top of your head. So I'd rather do that. At one point during the fall, air resistance is 540 newtons. Calculate the resultant force and hence the acceleration. Right. Okay, guys. Now let's think about it. Here's the skydiver. The weight of the skydiver, we know, 750 newtons. All right. Now, the air resistance is 540 newtons. Okay. Now, the upward force, because remember, air resistance or drag is always opposite the motion. So you're going down, your force is up. That is 540. Calculate the resultant force. Now, resultant force is really easy. Thank you, guys. I'm getting the correct answer. All of you. 750. Take away 540. That gives me 210 newtons upwards. Now, guys, listen. Many students just write 210 only. So they forget the units, capital N. Some do 210 and newtons, but they forget to tell the direction as upward. Oh, my bad. Downwards. Because 750 is downwards. My bad. Sorry, guys, I'm just correcting it, right? 210 newtons is downwards because 750 newtons is a larger force. So large, take away small, 210 newtons down. Now, that's the first part, resultant force and the acceleration. Okay, to find the acceleration, I need to write F equals ma. Guys, let me tell you one thing here. There are two formulae that you use acceleration in GCSE Physics. One of them is F is equal to ma. The other one is A equals V minus U over T. There's a third one, actually. V squared minus U squared equals 2AS. Now, here's the thing. Tomorrow in the exam, if there was a question and it involves calculating acceleration, you know it's one of these three. Thumbs up if you understand this. Yeah? If there was a question and it says to calculate acceleration, right, it will be somehow one of these three, some sort of a variation of these. Right, cool. Now, in this one is F equals ma. Resultant force is 210. M of this guy is 75 kilograms. A. Oh, that's really easy. All I need to do is 210 divided by 75 gives me the answer 2.8. Acceleration is 2.8 meters per second squared. And thank you, Medha. Downwards. Listen up, guys. The direction is so important. Acceleration is a vector. Remember, we just discussed that, right? It's a vector, so you have to show the direction, right? One might say, oh, the question doesn't really ask for the direction, but you need to know. If it is a vector, direction you need to say, for sure. Any questions up to this point? No. Good. The skydiver later reaches terminal velocity. Explain in terms of forces why terminal velocity increases when the parachute is closed compared to when it is open. Right. Okay. Listen. I'm just going to delete this one now. Right. So, when the parachute is open, now let's say this guy is, here's a parachute. You know, when you first jump off a plane, it is like a backpack, right? It's at the back of the person, like a backpack. It's not open. Then, further down, when it is the correct height, the guy opens the parachute. Now, it is open. Now, if you remember the velocity time graph for a falling parachutist, guys, this is an exam hotspot. You can get a lot of questions on it. So the guy starts from zero, the person starts from zero, accelerates, but the acceleration reduces with time and then comes to sort of a constant. Now this is the initial drop. Like with the parachute on, the person accelerates, right? And it goes like, to a certain velocity. This could be probably about 50 meters per second. It's pretty high speed. Nobody can land with that at that terminal velocity. It will be quite terminal if that person does. So you know what they do? They open the parachute. Opens the parachute. Now, when the parachute is open, there's a significant reduction in the downward velocity because of the resultant force being upwards. And then what happens is the guy comes to another lower terminal velocity. Now, this could be like 5 meters per second or something. That's okay. And the person lands with that. That is the full drop, guys. And sorry about the, my video is kind of cutting this. So let me move it to this side. Here's the full drop. Now, I'm not even giving the answer to part C. I'm just explaining it. Look, region of initial acceleration when the person jumps off the plane. Then the high terminal velocity achieved when the parachute is still closed. Then the person opens the parachute. Then you have a region of significant deceleration. And then the person has this low terminal velocity too. And then the person lands at this point. Landing. That's it. Is that all good, guys? Yeah? Right. Okay. Now let's have a look. Now this question, I just explained the whole scenario so that I can kind of, you guys get the full picture here. Now let's go to the next one. The skydiver later reaches terminal velocity. Explain in terms of forces why terminal velocity increases when the parachute is closed compared to when it is open. So the question's wording is not the greatest, guys. So what they're asking is, when the terminal velocity here, when the person's parachute is closed, is higher, the terminal velocity here is lower. This is 50 meters per second or something, 55. This one is like 5 meters per second. The question, Anika, I see your question, is asking, why is this higher than this? The reason is the drag is much larger in the second situation, isn't it? Right? So in terms of forces, you can say let me just write the answer here, guys. Yeah. So it's different, basically. So it's higher first and then it decreases. That's why the wording is not the greatest. So let's say the weight is the only downward force and that remains constant. The drag depends on the area and it increases when the parachute is open. So the terminal velocity is higher when the parachute is closed and vice versa. Close, right? Because the person will accelerate and then the same drag, because the drag depends on the speed, right? So if you are traveling faster, what happens to the drag? The drag is higher. So here, for the drag to be equal, this is the exact part, right? For the drag to be equal to the weight, you need to travel at much higher velocity if the area is low. Why the area is low? Because in the second situation, you have the area of the parachute. Does it make sense? So tell me, I don't know, just maybe give me a letter Y in the chat if you understand this question, guys. It's a very popular exam style question, right? First part, calculation, W equals mg. Second part, calculation, F equals MA resultant force. Third part is an explanation question. If you have any questions, you can ask me. Grace, the graph, he is always decelerating depending on the direction you're looking at. Actually, he is actually accelerating first. No, he's not decelerating. Can I clear the board now? Let me get the graph back again. Actually, I might have a better diagram of that on my teaching notes. Just give me a second. If I can quickly pull that up, it might be better rather than drawing it again. Terminal velocity. There you go. Right. This is it. My tutors, you might actually recognize this from your theory notes, right? That I've used this one. So here's the full story, actually. Grace, you asked about it, right? Now think about, this is not a, actually that's not, this is just a normal one. Let me just get the falling parachutist one exactly. So that is exactly what you guys asked me. Here. Right. Now, the person jumps from the parachute, and initially, the only downward force is weight. So, the person will start to accelerate. In a little while, the drag starts. Drag is opposing motion. Still, the weight is greater, so there is acceleration. The person gets faster and faster and faster until the weight and drag are equal and opposite. So, what will happen? The person will come to a terminal velocity. So this is the initial acceleration region, and reducing acceleration, and then acceleration becomes zero. The yellow region shows when the person goes at that constant, let's say 55 meters per second or something, for a certain period of time. And now, at this point, the person opens the parachute. Now, then only the deceleration starts, because the person starts from zero, accelerates, constant velocity, then here's the deceleration, and then comes to a lower terminal velocity, again a constant velocity, and then lands. Does that make sense now? Guys, thumbs up if that makes more sense. Some sort of a reaction. Any reaction, I think, will do. I think I allowed reactions in this thing. Just do it to see if that's working. Good, good, good. Thank you, guys. Okay. Good. Right. Okay. So, it is a common question, Vishal. Yes, you can get that. Right. So, guys, if anybody joined just recently, we are just walking through some of these most common exam questions that you can get in your exam tomorrow. So, for combined people, it's the ones that are in, the lighter color. The green bit is for triple. In fact, everything is needed for triple. If you are doing triple, you need everything. If you're doing combined, you just don't need the green bits. Right. Let's do another question now. So I'm doing questions and running a timer so that you guys can try this. Right. This one is a very popular GCSE exam question, guys, about the velocity time graphs. Say yes in the chat if you have seen velocity time graphs in previous past papers. Why? Just why. Letter Y is fine. Why for yes, guys? Throughout the chat, why for yes, in for no. That's enough. Yeah. Thank you, Shah. Yeah. There you go. Right. Guys, we have done a lot of velocity time graphs in our past paper class. Right. We've done close to 20 papers altogether. So we've done a lot of these. Yes. That's all right. So everybody, let's give this a try. Now, I will need to draw the diagram for this one. The velocity time graph of a car shows it accelerating from rest to 24 meters per second in 8 seconds. Okay, let's draw the diagram first. I'm going to let you guys try this one, but I'm just going to draw the graph, velocity time from rest to 24 meters per second. In 8 seconds. Okay, so we know 0 here 8 here. Okay. Traveling at constant speed for 10 seconds. Okay. In constant speed here for 10 seconds. So that's 18 because 8 at 10. Then decelerating to rest in 4 seconds. Right. That's 22 seconds it comes to the rest. Thumbs up if you have seen graphs like this before. Or send me letter Y. Thank you, Sihas. Good. Very popular exam question, guys. So let's try this one. So I'm going to give you about 2 minutes to do the rest of the question. Timer's on, guys. So let's do that. Okay, this is a try. I will answer it. I will do the full, the rest of the question in a bit when the time is up. Thank you, guys. Yeah, please send me the answers, guys. Right? Do not just just do it yourself. Just send me the answers in the chat so I know. Right? When I have the answers in the chat, I can see what you got. Thank you, guys. Okay, everybody, please send me the answers in the chat. 40 seconds more, and I'll do it. In the meantime, if there are any particular things you need to do, just let me know. So we are starting from here, and then we're just doing the questions on, we are going to go to waves in a bit, then magnetism, all that. And I know most of you need help on magnetism, so I'll definitely do that. Yeah. Time's up, guys. Let's have a look. The velocity time graph of a car shows these details. We'll mark it. Calculate the acceleration in the first 8 seconds. Somebody tell me, what's the formula for acceleration? Or how do you find the acceleration from a VT graph? How do you find the acceleration from a velocity time graph? Tell me. Gone? What feature of a velocity time graph gives me acceleration? Gradient. Thank you. Yeah. So acceleration is the same as gradient. So what's the gradient? 24, which is this height, divided by 8. And the answer is 3 meters per second squared. That is the acceleration. Calculate the total distance traveled. Now, we did this in maths as well. And most students would find the area of the triangle, and then you find the area of the rectangle, then you find the area of the triangle and add them up. And you can definitely do it, but I would personally treat this as a trapezium. So area of a trapezium is A at B divided by 2 times perpendicular height, right, guys? So area is A. So one of the sides here, that is 10. And this one here is 22. Divided by 2, multiplied by, what's the perpendicular height? 0 to 24. The perpendicular height is 24. So all I need to do is 10 add 22 divided by 2 and multiply that answer by 24, and you get 384 meters. Thank you. We were fun. You got the right answer. And thank you, Isa. Is it T1 Isa? Yeah, I got the right answer. Guys, if you did it using the area of this and then area of this and area of this and adding them all up, isn't this much easier? Thumbs up if you agree, or do any reaction if you agree. Right? There's heart reaction or any reaction. 100%. I don't know anything. Yeah, there you go. Right? So please save your time, guys. Learn to do it this way. But sometimes, if you don't have all the information, especially if they're asking about the displacement in the first part only, then you'll have to do that one, right? Don't worry about it. If you use a trapezium, that's very good. Yeah, great. Next one. This is a good one. Anybody? Okay, got some answers already. Let's have a look. I'm just deleting this so that I have more space. Yeah. Now, part C says the braking force in the final 4 seconds is 6,000 newtons. Calculate the mass of the car. So, guys, there are a couple of different ways of doing this, right? In the final 4 seconds, I can find the deceleration. How do I find the deceleration? It's a gradient. Okay. So the height here is 24 divided by 18 to 22. This is 4. Okay. 24 divided by 4. So we know the deceleration is 6 meters per second squared. Right? So I'm trying to find, F is equal to ma. Right. So the braking force is 6,000 newtons. I don't know the mass. Acceleration is 6. Okay. Obviously, you divide both sides by 6, divide by 6, and I know the mass is 1,000 kilograms. Yeah? Does that make sense, guys? Thank you, Vishal. Yeah. Thank you, Isa. Thank you, We Bear Best. Okay, all right, Lof, you're giving me the correct answer. Mukesh, okay. So you can use this to do that, right? There's another way of doing this, right? There's another way of doing this. That is, I'll show you that as well. Work done is the same as kinetic energy. Why is that? Because when the car is slowing down, the brakes do work against it. So the work done is equal to kinetic energy, because when all of the kinetic energy is gone, that's when it stops. So work done is force multiplied by distance is equal to kinetic energy is half mv squared. Okay. Force 6,000. What's the D, guys? D is the area here, right? This area here, because it's the deceleration part. So how do I find the area here? It is base is 4 times 24, base times height divided by 2. So 24 divided by 2 is 12 times 4. That's 48 meters. Okay. So this here is my D. So let's put 48 here is equal to half times by mass you don't know, V. When you started it here, the velocity was 24 squared. Now, move the 2 to this side. 6,000 times by 48 times by 2 divided by 24 squared. Let's see what you get here. 6,000 times 48 times 2 divided by 24 squared. Beautifully give me 1,000 once again. Can you see that, guys? This is an alternate way of doing it. It's a slightly tricky method, but yeah, I first did it using F equals ma. I did using the second method now. Yeah? Is that all good? Don't worry again too much about this one, guys. If you didn't understand one of them, if you did understand the other one, you guys are fine. Yeah? You guys are all good. Good. Right, guys. Let's quickly have a look at the next part now. So F equals ma, all done. Let's do a question on have the same question twice. Sorry about that. Elasticity. Remember Hooke's law? Right. This question is about that. So everybody, let's try this question. I'm going to give you again about, I would say 2 minutes is fine. If you need a little bit more time, I don't mind extending it. But for the time being, we'll start with 2. Great. Let's do this one, guys. Question number 4. Hooke's law, elasticity. Let's do this. Yeah. And in the meantime, if anybody wants any questions, any theory talk through, let me know. But I know magnetism is something that many people need to work on. I will be moving to magnetism like soon. Okay, I will be discussing about magnetism soon. And in the triple only section, I'm going to discuss more about electromagnetic induction. In the combined section, I'm going to discuss about Fleming's left-hand rule and all that. And also the DC motor, which is a very popular question. About 35 seconds now, guys. Send me the answers, yeah? The spring constant, so I can see how you guys are progressing, right? You don't need to send me the method, guys. Just the answer is fine. A, answer. B, answer. That's enough. Any explanations, you can keep it really, really short, okay? In the exam, you wouldn't do that, obviously, but here you can. Thank you, Grace. Yeah, good, good, good. Right, guys, we are going to discuss this one now. Right, let's have a look. Okay. A spring is compressed by 0.04 meters, that is my extension, and it stores 0.032 joules of elastic potential energy. Okay, calculate the spring constant of the spring. Now, guys, remember, the spring constant, there are 2 formulae. Sorry, elastic potential energy, there are 2. Half Fx or half kx squared. Now, I have seen some people kind of get this modeled up and they go with half Fx squared. That doesn't exist, right? It's either half Fx or half kx squared. This comes from the area under the graph, by the way, right? Now, we need to calculate the spring constant, k and x. Obviously, I have to go with this version, right? I'm not going to go with F because I don't have the force. But look, I have x here. I have k here. Yeah, E or X, they're both okay, yeah? E and K, K and X, I have to go with the second version. So, elastic potential energy is 0.032 is equal to half times F, half Kx, K, I don't know, times X is 0.04 squared. So, let's simplify this one. I'm just going to move the 2 to that side. 2 times 0.032, that's gone there, is equal to k, and this 0.04 squared, I'm going to divide to this side. There you go. Let's put this in the calculator. 2 times 0.032 divided by 0.04 squared gives me the spring constant to be 4T. You got this one right? Thumbs up? Or any sort of thing? No, not yet. No matches obviously. No. Um, yeah, send me the answer. Anybody got 40? 40 newtons per meter, guys? That is the answer. Yeah, well done. Right. Part B. The spring is used to launch a 0.02 kilogram ball vertically. Oh, right. Okay. So you have the spring and you squash it. It's like, those toys, yeah? And then you just keep this is the mass, and it's launched vertically. Assuming all elastic potential energy converts to kinetic energy, calculate the speed of the ball. Oh, so kinetic energy is half mv squared. Now it says all of the elastic potential energy becomes kinetic energy. Okay, so if elastic potential energy is 0.032, kinetic energy is the same. Okay, 0.032 is equal to half times what's the mass here? 0.02 times b squared. All right, let's simplify this one. I can divide this one and I get 0.01. So 0.032 divided by 0.01 is my v squared. How do I get v now? I need to root it. Okay, so let's root this one. That should give me my v. So the calculator, square root, fraction button, 0.032 divided by 0.01 gives me 1.79788, call it 1.79 meters per second. Who got this one? Hello? Anybody got this? Kinetic energy is half mv squared. Kinetic energy is the same as EPE. 0.032 is equal to half times m is 0.01 times 0.02 times v squared. And I just simplified this one and I got that answer. Well done. 1.788. Yes, 1.7878. I'll be a little careful because it's 7888. Yeah. So I would try and round it to 2 decimal places. So 1.79. Well, it's not a big deal. You're right. Done. Calculate the maximum height the ball could reach. State one assumption. Right. Now, so you have this spring, and then you launch this object, it will go up, but it will not go up forever. It will go up and stop and fall back. So the question is, how high does it go? So there are 2 different ways of doing this, guys. The easier way would be to think about energy approach. So kinetic energy lost as it goes up is equal to gravitational potential energy gained. Okay. Kinetic energy lost is 0.032 because we just know that from here. The question says so. GPE is mgh. Let's substitute, guys. G is 10 times h. 0.032 divided by 0.02 times 10 is your height. Let's do that. The answer here is 0.16 meters. Well done. I got correct answers from We Bear, Bears Fan, and then Isa Monkey, and yeah, okay, that's good. That's good. And yeah, earlier as well. Well done. There's another way of doing this considering equations of motion, but that's a little bit touching A-level side, so let's leave it, okay? This is enough. State one assumption. The assumption is no air resistance, no drag. All of the kinetic energy is fully converted into GPE. questions sometimes say we shall to give it to two decimal places or significant figures. Sometimes they don't. So if they do, you go with that. If not, no. Yeah, I'm actually originally Sri Lankan. Like I know, like because I used to work in a school in Whitechapel, which is like about 96% Bengali. So yeah, they also thought that I'm from from there. Yeah, yeah. Yes, usually, Grace, they will mention it, or but no, mostly for the convenience, you don't go with that. You just consider this to be, you just consider this to be this way. Yeah, but it's okay. Right, guys. Now let's do some waves questions, shall we? So this question is about waves, okay, sound waves and all that. If anybody wants any quick recap on any theory stuff related to waves, you can let me know. And yes, Zaina, I'm going to, like, we started with forces and now we are into waves, and then I will move you guys to magnetism too. I know it is something that many people need help on. And guys, we might from the look of it, we'll see if it's been an hour already, but we still have a little way to go. So we might go a little bit to yeah, yeah. Okay, let's have a look. Right, let's quickly try this question, guys. I'm going to leave this for um, maybe, as usual, I'll give you 2 minutes first. Uses and EM waves and the risks is something I think it's quickly something you can quickly look up actually, right? So for users, you need to think about the full electromagnetic spectrum, and you need to think about what they are used for, right? For example, visible light is something that many people forget. They'll be like, apart from seeing, people are like, what else can I write? So you can talk about photography, you can talk about using for microscopes, telescopes, all of these things, visible light. Then microwaves, you can talk about satellite communication, mobile phone communication, cooking, all that. I'll have a look at it. Yeah, we're good. Yeah. Okay. About a minute left, guys, for the second one now. Thank you. Guys, one thing you can do for me, I mean, if you're here and if you're getting value from this, just maybe consider just liking this, and maybe if you're not subscribed, just subscribe. I'm just trying to kind of put some effort to grow the channel, and that'll be helpful to me. Thank you, guys. $15 more. Thank you. Good. I'm getting the answers now. Okay, time's up, guys. Let's have a look, shall we? A sound wave travels through air at 340 meters per second with a frequency of, okay, this is your V and this is your F. Calculate the wavelength. Oh, that's very easy, guys. V is equal to F lambda. 340 is equal to 680 times lambda. So lambda is obviously 0.5 because that's double that. So 0.5 meters. That is the wavelength. Calculate the period of the wave. So remember, periodic time is 1 over frequency. Frequency is 1 over periodic time, or periodic time is 1 over frequency. Now, that will be 1 over 680. So all I need to do is 1 divided by 680. You get 0.0015 seconds. That is the periodic time. 0.00147, 0.015 will do that. That's enough. Or you can write in standard form 1.5 times 10 to the power of negative 3, or you can write as 1 over 680 seconds. They all work. Good. The same sound wave enters a solid material and its speed increases to 5,100. Now, guys, in solids, particles are much close together. When particles are close together, the sound or waves travel much faster through it, right? Back in the days, long time ago, people apparently used to, like, there were trained people. I've heard that the people used to, like, put their ears to the ground to listen for the marching armies. Why? Because before you hear it through air, you will hear it through the solid ground. Yeah, I'm Sri Lankan actually. To play. Originally, I'm Sri Lankan. Been here. I've been in the UK for 16 years now, but I'm originally Sri Lankan. Yeah, 15, 16 years ago, I came here to do my masters. Yeah, okay. Yeah, I'll have a look at it. Yeah. No, listen. No, it's fine. Yeah, many people. Yeah, we are all very close. So, right. Now, in solids, it travels much faster. The frequency remains unchanged. Calculate the new wavelength and explain why the frequency does not change. Okay. Now, guys, again, what do we need to do? V is equal to F lambda. Now, why V is 5,100, F is 680 times lambda. So, what do I need to do, guys? 5,100 divided by 680 gives me 7.5 meters. That is a new wavelength. Yeah? Good, right? 7.5 meters. Now, why frequency does not change? Because frequency is a property of the source of the sound. Now, look, if I'm talking here, and just because it goes through a solid wall, on the other side, if people can hear me, it doesn't really change the frequency, does it? Right? So frequency depends on the source, right? So the frequency is a property of the source of the sound. That doesn't change because it goes through a material, a medium, really. Done. Yeah. Okay. Yes, Bindu. Yeah, they're very popular. Both surnames you mentioned are very popular in Sri Lanka. Yeah. I think they are sort of linked to some Portuguese lineage, but yeah, very popular. All right, guys, let's go to electromagnetic waves. As you can see, earlier today, I finished some lessons and I was prepping for this session and I got questions from like different parts to represent different things. So I'll cover as much as we can. Yeah. Right. We are still kind of doing the combined stuff, not combined only. There's nothing combined only. Combined and triple both content, guys. Looks like we might go a little, a bit after the initially planned time. But yeah, just to give you a little bit of heads up. Right. Okay, cool. Let's try this question, everybody. This is about electromagnetic waves. As usual, I think just gonna run it for 2 minutes first. Now I know sometimes this time may not be exactly enough for you to finish it, but because this is live and this is for your exam tomorrow, and we are doing a fast-paced revision, that is yeah. Are they actually like those Mendes and Fernando are like some names that are connected to Portuguese lineage, and then because of the colonization and that time, those names are still very popular in Sri Lanka, in Tamil Nadu, yeah, places like that, in India, Sri Lanka, yeah. About a minute and 20 seconds left, guys. These are like very standard GCSE exam questions from AQA. Yeah, please try this. Thank you, guys, for those who responded to the video thing. Good. I'm in Aylesbury, actually, Isa. In UK, I live in Aylesbury. That's in Buckinghamshire. Yeah, I used to live in Harrow for a long time because I used to work in a school there. But about 5-6 years ago, I moved to Aylesbury, so that's where I'm from now. Where are you guys from? Message me. I know I asked the other day. Where are you guys from? Like which part of UK? I remember in the previous ones there were people from Hull, people from Portsmouth. Okay, good. People from Birmingham, Harrow. Sanadi. Yes, okay. London, North, which Northwest. Okay, good, good, good. Hull. Okay, good. Yeah. Thank you for the answers, guys. The time's up. Let's have a look, shall we? Hey, Hayes. Okay, yeah. Okay. Jude. All right. London. Good. Let's have a look. A radio wave has wavelength of 1,500 meters. All EM waves travel at speed of light. That's your V. Calculate the frequency of this. Okay. So V is equal to F lambda. And V is 3 times 10 to the power of 8. F, I don't know. Lambda is 1,500. Now what do I need to do? 3 times 10 to the power of 8 divided by 1,500. That gives me the frequency as 2 times 10 to the power of 5 hertz. A microwave has a frequency of 2.4 times 10 to the power of 9 hertz. Calculate the wavelength. Okay, part B. Again, V equals F lambda. Because all electromagnetic waves travel at the speed of light, and the frequency is 2.4 times 10 to the power of 9 times lambda. What do I need to do? 3 times 10 to the power of 8 divided by 2.4 times 10 to the power of 9 gives me my lambda. So let's quickly do that. 3 times 10 to the power of 8 divided by 2.4 times 10 to the power of 9. And that gives me 0.125 meters. That's it, about 12.5 centimeters. Yes, that's typical microwave wavelength. Yeah. Grace, we are supposed to go finish around this time, really, but I'm still a little behind with the thing. So we might go a little over the time. So I'm going to move to magnetism now, actually, which is still combined. And then I'll go to triple on this stuff. Guys, can I ask you something? If you are combined science, can you send me the letter C? I just need to see roughly how many people are there for combined. If you are combined science, just send me letter C. Thank you. Thank you. Yeah. Okay. Right. Okay. So these are all combined and triple content, right? Still, we are still there. Right. compare the radio wave and microwave in terms of frequency, wavelength, and energy. State which carries more energy per photon and explain why. Photons is a little kind of an A-level touch, so don't worry about the word photon too much. Just go with energy. That's fine, okay? Let's have a look, shall we? Now, we need to always look into the question to see what it is asking. In terms of frequency, now which one has a higher frequency? Obviously, microwave, right? So microwave has a higher frequency compared to radio waves. What about the wavelength? Microwave has a shorter wavelength, right? Hello, Les. All right, good to see you. Remember from yesterday? Microwave has a shorter wavelength compared to radio. Radio is 1,500 meters. That's about 12.5 centimeters, isn't it? So the wavelength of microwave is shorter than that of radio waves. Now, guys, in terms of energy, remember, the higher the frequency, the more the energy. That's obvious, right? This is really because there's a formula called E is equal to HF, right? E is proportional to F. H is something called Planck's constant. Not in your spec, guys. You just need to know higher the frequency, the more energy, obviously, right? Yeah. Let's do this one. Much shorter than radio waves. Okay. Wavelength and energy. Energy of microwaves is higher than that of radio waves. See, I just explained about all of them. Done. Yeah, all good? Yeah, I'm good, Les. Right? How are you guys? Right, thumbs up or give me some sort of a reaction if you understand everything on this question. Yeah, very like the question you can get about this electromagnetic radiation and stuff. Yeah, good. Right. Now, let me clear the board. Guys, you need to know the electromagnetic spectrum. Like, you don't need to know the exact frequencies and stuff, but at least you should know the order of this one, right? Yeah, I remember you here from yesterday. Yeah, you said you'd come today and you were here for the other one. I remember you. Yeah. Guys, listen. Violet, indigo, blue, green, yellow, orange, red. Some people use this mnemonic. Richard of York gave battle in vain. I don't know if it's actually related to some historical thing. I'm not really good in history, but Richard of York gave battle in vain. Now, next to red, after red, infrared. See, makes sense, right? Red, infrared. Before violet, ultraviolet. See, it's all logical. And here we have X-rays, gamma rays, and cosmic rays. And on this side, we have microwaves, radio, TV waves, TV and radio. Yeah. Right. So you just need to know this in order. Like sometimes I've seen in exam questions, they might give you, TV waves are like, sometimes that it's a part of the radio waves, right? It's considered like that. That's okay. Sometimes I have seen exam questions where they have given like this is out, this isn't there. Let's say this isn't there, and then they just ask you to fill the gaps or something, stuff like that, right? Just good to know those things, right? Just in case, right? So anyway, this is all you need to know, right? There is a mnemonic to memorize this. That is, there are multiple of them. So one of them is red Martians, people from Mars invade Venus using X-ray guns. Yeah. Cosmic rays are the rays that are coming from outer space. So red radio, again, these things can be considered one. Martians, micro, invade, infrared, Venus, visible, using ultraviolet, X-ray, X-ray, guns, gamma. If you want, you can use that, right? And for this one, Richard of York gave battle in vain. So in vain. Some people use this as a name, as Roy Gibiv, as a name of a person. Yes, that's why I saw, right? TV is a sub part of the radio. So you can split it or you can consider together. It's fine either way. Right? So some people use it like that. Roy Gibiv. Red, orange, yellow, Roy, as a name. Roy is a common name. G, like the whatever the middle name of the person. Biv. B-I-V. Okay. Right. That's enough from that one, guys. Now let's quickly go to this one. Another question. Okay, magnetism. So this is something that I know many people asked. So let's have a look, shall we? I'm going to give you a couple of minutes. Maybe this one requires about, it's an explanation one. So maybe 3 minutes, I think. Actually, I'll run 2 minutes and I'll give a little bit extra time at the end. Right, let's do this one. This is magnetism, guys. Yeah. Yeah. So the radio wavelength has a longer wavelength, but the lowest frequency and vice versa. Yes, Grace. I will go to motors in a bit. I'll explain the how the Fleming's left-hand rule can be used to explain the rotation of the motor and the function of the split ring commutator. Yeah. We bears, I would rather connect the energy to frequency. Yeah. Because there's a formula called E equals HF. That's what it is really connected to us, not in your specification, but the higher the frequency, the higher the energy. Yeah. I will go through Fleming's left-hand rule. Yes, he is a part of the plan today. Definitely do that. Yes. Thank you, guys. I don't know. Let's do that. Yeah, we have a lot of elephants in Sri Lanka. Yeah. That's right, Isa. Yeah. Right. I think that's probably enough time. Let's have a look. A student places an iron nail near a bar magnet. Okay. So there's an iron nail. There's a bar magnet. Now, what happens is when you bring a magnetic north pole, it will induce a south pole here, and it will just pull this in, right? So explain the difference between a permanent magnet and an induced magnet using the iron nail as an example. Now, guys, I'm going to tell you the answer. So a permanent magnet has a north pole and a south pole, whereas an induced magnet is a magnetic material which is made of iron, cobalt, and nickel, and it acts as a magnet only when it is in the magnetic field from outside. So if you bring another magnet from outside, it will act as a magnet. Also, a permanent magnet will attract or repel with another permanent magnet, whereas an induced one will always be attractive. Because if you bring a north pole, it becomes south and attracted. If you bring a south pole, it will become north and attracts to it. Got it? The student removes the magnet, explain what happens to the magnetism of the nail and why. Now, when this magnet is removed, this also loses its magnetic properties. It's not a magnet anymore because it is not in an external field, right? There is nothing. There are like things called magnetic domains inside these things. They change, and that's why they magnetize and demagnetize, but not in the spec. But you get the point, right? Sketch and describe the magnetic field pattern around a bar magnet, including the direction of the field lines and where the field is stronger. So a few things here I need to tell guys. One, this is a bar magnet, north pole and south pole. Now I'm going to draw a deliberately a wrong diagram. You tell me what's wrong with this, okay? Right. I did this deliberately and it's wrong. Can somebody tell me what's wrong with this? Something is wrong. What is wrong? Gone? The line in the middle like that? No, it does not. Inside the magnet, you don't need to draw them. You do that in solenoids, but not here. No, that's not it. Go on, guys. Keep on trying. What is wrong with this diagram? This diagram is not correct for a reason. Why? No, it is actually from north to south. It starts from north. It is going from north to south, isn't it? It's going from north to south. That is not wrong. You can add multiple lines, Mukesh, but that doesn't make it wrong. I can draw more, Isa, but that does not make it wrong. At least I've got one line on each side. There is something wrong on this. Right. No? Listen. This is what many people... So I did this deliberately because I don't want you to do it tomorrow. The wrong thing is that these lines are crossing over here. Magnetic field lines never intersect. Remember that? Thumbs up or give me some sort of a heart or some sort of a emoji if you remember. See? The reason why I did this, guys, I've seen people doing this all the time. So I did it deliberately wrong. So how do I draw the correct one? It's better if these are nice and symmetrical, but at least something like that. Does that make sense, guys? Yeah? Good. So remember, they should not cross, right? Well, the reason for that is because the magnetic field lines, each line shows the resultant force at the given point on a tiny magnetic north pole. Now, the resultant force is only one. You can't have two resultant forces because if they are crossing, they are showing it's one this way, one that way. That's wrong. You don't need to understand that, guys, for GCSEs. That's more like A levels. The point here is they shouldn't cross. So, sketch and describe the magnetic field pattern on a bar magnet, and you can say it is strongest at the poles. This pole here and this pole here. How do you know when it is strong? If the lines are close together, it is strong. A strong field is when the lines are close together. Look, the lines are closest at the poles. I remember a GCSE exam question that I did just recently with one of my classes. I don't remember whether it is Edexcel. I think it's AQA class yesterday. No. It was Edexcel past paper class I did yesterday. Yesterday, yes. That question literally asked the students to show, put an X where the magnetic field strength is strongest. So you need to put an X here or here. Those who are in the in Excel class probably can combine. Yeah, that's what something. Yeah, remember? Yeah, I can't show. I have the question. It's just on that live on YouTube. I can't show the actual question from in Excel. You get the point. There you go, guys. Done with that. Let's go to another one now. Listen. Let me quickly explain this Fleming's left-hand rule thing, because a lot of you asked about this one. Now, guys, listen up. What Fleming's left-hand rule says is, look at my left hand. If I keep my three fingers of the left hand, thumb, first finger, and second finger, in a direction that are perpendicular to each other, like that. They're all perpendicular to each other now. They show FBI, as in, Federal Bureau of Investigation, FBI. F for force, B is the magnetic field, and I is the current. FBI. Now, this can be used to find the direction of the force. Let me give an example. Say you have a current carrying conductor like that, and the magnetic field is going into the plane of my board. Now, this we normally show by putting crosses. Now, this really comes from thinking about an arrow. So if I shot an arrow, and if I could see the leaving arrow in slow motion, I would see the cross at the back, which is the idea, where it's come from, right? Now, yeah, thank you, guys. Okay, so FBI. Now, what is the direction of the force? Now, look, I'm just going to arrange my B's into the plane. Okay. Now, I need to not move that finger, and I need to move my current upwards. Oh, the force is to the left. Give me some sort of a sign, guys, if you understand it. The force is to the left. Yeah, maybe emoji, some sort of an emoji, if you understood, right? That is the Fleming's left-hand rule. So if you want like a proper wording of it, this is when the first three fingers of your left hand are perpendicular to each other, such that the first finger shows the direction of the magnetic field, and the second finger shows the direction of the current, the thumb is in the direction of the force. That's the full statement of Fleming's left-hand rule, the motor effect you call it, but simply FBI will do the trick. FBI. Magnetic field is going into the plane here. Right. Now let me explain how a simple motor works. Now, this has a rectangular coil. I mean, you can have loads of them, but let's say one here to understand the concept. And here we have a magnetic north pole. And on the other side, we have the magnetic south. Okay. Now, the field is from north to south. Now, we know that. Okay. Now, you connect it through a split ring commutator. I will explain this in a bit, guys. Okay. Split ring commutator to a DC supply. This is a DC motor. Now, what happens is this sends a current through this, through that. Current is going that way, and it goes like that, and it is coming through that. Now, let's pay attention to this one here, right? The one at the far end. So FBI. So B is this way. Now, I can't change that one. I is that way. Oh, the force is downwards, guys. Send me a message in the chat saying with letter Y if you understood why it is downwards. The force on this side is down. Yeah. Right. What rays are we referring to here, Grace? Yeah. So that's the first one. Now think about this one. So the force is coming this way. So FBI. So B is still this way. So B is this way. I is this way. Now where's the force? The force is upwards. Okay. So this one here is up. Now you can clearly see there's an upward force on this side, downward force on this side. So what will happen? It will rotate in an anti-clockwise direction. Right? If I think about my calculator here, right? Imagine this is the calculator. This is the calculator. Imagine this is the coil. And one here's an upward force. On the other side, we have a downward force. So what will happen? It will rotate like that. Right? Send me a message in the chat if you understand it. Yeah? Right. So this is the idea behind the DC motor. Now, what is the point of this split ring commutator? This is what we call the split ring commutator. Now, the whole point of the split ring commutator is to make the motor keep on turning in the same direction, right? Now, imagine, to explain the importance of the split ring commutator, imagine if there wasn't one. If there wasn't one, we have a big problem. Here's the problem we have. One of the problems. We have two problems, but let me just tell you one first. Let's say they are connected like that. Now, no split ring commutator, you're just connected to a power supply. Now, even if you somehow manage for this to, turn it, after a little while, this will all get twisted up. Thumbs up if you have done this problem. If you just rigidly connect it and if you start to get it to turn, it will all get twisted up, wouldn't it? That is one problem, right? Right? So you can't really connect it to rigidly like that. You need to have an arrangement like this one, where there is where it would slip. Now, the other problem is this. Now, let's say you start like this. Now, the current is that way, and this current is going that way. Now, after one half turn, it would look like this. Yes, after one half turn, it looks like this. Now, the current is going like that. Oh, look, we have a problem. Because previously, current was going that way, and now the current is going the other way. So what will happen? Instead of turning like this, it will go just like that. Thumbs up if you understand it, or maybe say why in the chat. Right? If you just normally connect it, it would just go like this back and forth. It's not going to really work, right? So what do we do instead? Instead of having it like that, so these are the practical problems that you have if you didn't have a split ring commutator. The split ring commutator here, what it does is when it turns 180 degrees, so the split ring commutator is like this. So for half the time, the wire is in contact with this, and then it will switch to the other one. So, in other words, at any point, any wire that comes to the position covered by colored in green will always have a downward force. Any wire that comes to this position highlighted in yellow will always have an upward force, and this bit is free to move. That is the point of the split ring commutator. Guys, send me any questions if you have anything about the DC motor. Yes. So if you change the terminals of the power supply, you can, that is an exam question actually. Grace, thank you. Right? If you change the terminals of the power supply, the current, the motor will spin the other way around. Can someone tell me another way of changing the direction without changing the power supply? There's another way. In a simple one like this, how can you make? What can you do to make it go around? Reverse the no. Reversing the battery is the same as the power supply. Change the magnets. Well done, Jude. How do you do that? Yeah, yes, right, Anika. That's what you do. You switch the north and south poles, and it will start to go the other way. Understood? Right. Now, in real motors, you have more than one turn, so you have a greater force. Also, the turns are not exactly in one like rectangular shape. They are more they're in all different angles. So at any point, there will be some which will feel this maximum force. Right. I think theory-wise, that's enough, guys. Yes, generators are in triple only, we show. We can have a look at that. All right. So if you weren't here, I mean, I accidentally opened this one, but these are the things that usually come up in lot of exam questions, guys. Anybody who is new, anybody who just came just recently, have a look at it. The ones that are in green are the ones that you get triple only, but the other ones were combined. Yeah. Right. Here's the question that I just got, right, guys? Let's do this one, and I'm going to give you about, again, maybe 2 minutes and a bit. So I'll run a timer for 2 minutes, and I'll give a little bit of more time as well. Let's do this one, guys. So yes, I'm still doing the bits that are for both combined and triple. I will go to some of the triple topics in a bit, guys, probably after this question. Yeah. In the meantime, if you are combined and if you need any particular help, tomorrow is the last paper. It's so just ask me in the chat. I can explain any theory part really quickly, or I can explain, answer any questions you may have about different question types or anything really. Thank you. Yes. Thank you for sending the answers through the chat, guys. Well done. Right, another 50 seconds left, and I will answer both questions, A and B. Yes, Newton's first law and second law are both in paper 2 because they are in forces topic. Yeah, I don't have all the written. I mean, I have some of them, but I can't really show them here on YouTube, actually, Isa. But I think the best way to do this is if you just do, just like search it AQA GCSE core practicals, they all do come up. Yeah. Right. Let's go to question number 1. A simple DC motor consists of a rectangular coil of wire placed between the poles of a permanent magnet. You guys just saw that. Yes, okay. Explain why a force acts on the coil when a current flows through it. Now, guys, this is an interesting one. Now, when there's a current flowing through it, why there's a force? Yeah, I could touch on Newton's laws of motion. We did questions related to that, but if you want me to talk through the theory, I can definitely do is we bear bears, and someone else also asked that one. Grace, yeah, you mentioned about Newton's laws. I can do that. That's fine. Fine. Let's write a good answer to this one first, shall we? So, explain why a force acts on the coil when a current flows through it. So when a current flows through a wire, I'll fix the spellings, guys, 1 second. It creates magnetic field around it. Remember the right hand grip rule. So if you have a current carrying conductor, I'm just going to use my charging wire here. Say this is a current carrying conductor. Imagine there's a current going in the upward direction. Now, if I hold it with my right hand like this, and the fingers now curl in the direction of the field. So I have magnetic field around it like concentric circles. Understood? Yeah? See? So what it says is the right hand grip rule. If you imagine holding a current carrying conductor with your right hand such that your thumb is in the direction of the current, fingers curl in the direction of the magnetic field. Understood? That's what it is. Now, when a current flows through a wire, it creates a magnetic field around it. This interacts with the magnetic field from the permanent magnets and a force acts. So this is the mode effect basically. Yeah. Guys, don't worry too much about whether it is magnetic flux or whatever. There are 3 different terms. There is like magnetic flux density, magnetic flux linkage. There are 3 very specific terms in A-level physics. Okay, but don't worry too much about that at this point, because you will not be tested on that in GCSEs. Yeah, right. So magnetic flux density is capital B. Yeah, I can tell you that. Yeah, that is what it is, right? When a current flows through the wire, it creates a magnetic field around it that interacts with the magnetic field from the permanent magnets, and a force acts on it. That's the answer for part A. And well done, Anika, you sent me something really very close to that. So I would give you, yeah. So mode effect, right? You can also mention that the force is according to the Fleming's left-hand rule. The 2 sides of the coil experiences force in opposite directions. Explain why this causes the coil to rotate rather than move in a straight line. Really good, guys. Magnetic flux density, Anika, is the flux through unit area. But that formula is not in your spec. There is an A-level formula called magnetic flux density is flux over area, not in the spec. So don't worry. Yeah, just know it's B, measured in Tesla. Right. The 2 sides of the coil experiences force in opposite direction. Now, guys, if you look at it, here we have an upward force. Let's say it's 10 newtons. Here's a downward force. There is a 10 newton. Now, what is the overall force in the vertical direction, guys? The resultant force, 0. Why 0? Because you have 10 upwards and 10 downwards, right? There is no overall resultant force in the vertical direction. Thank you, Grace. Yeah. However, because they are not along the same line, if they are same line, then it will like all cancel out. But what happens is now one is like that, the other one is like that. They are equal and opposite, but now they can create a rotational effect. Understood? It can create a rotational effect. Yeah. So yeah, this is called like equilibrium can be 2 ways. This is in translational equilibrium, meaning the resultant force, there is no resultant force, but there is a resultant moment. Yeah. That's part B, guys. Right. A lot of you ask about Newton's laws of motion. So let me quickly explain this Newton's laws now. Let me see if I can get a quick image from my notes. I can use that here. Look at this one, guys. Now, Newton's first law says that an object will remain at rest or continue to move at a constant velocity along a straight line if the resultant force on it is zero. Now, many people don't exactly understand it when you are told like that, and people just memorize it. But let me just break this down. Now, guys, think about a car parked on the side of the road. Flat road, the car is just parked. The weight of the car is 10,000 newtons. The upward force is 10,000 newtons. Equal and opposite, they cancel out. Resultant force is zero, and the car is not moving. That's one situation. So, an object will remain at rest, or that's the first part. Now, let's think about this. Say you are driving in motorway, and you're going at 70 miles per hour, right? 70 miles per hour constant. You're cruising. You just press the cruise control at 70. Now, you're going at the same speed, same velocity, let's say in a straight stretch of the road. The weight is 10,000, reaction is 10,000. Now, there is driving and resistance force, right? Now, if you are going at a constant velocity, your driving force should be exactly equal to resistance force. Now, listen. Let me tell you what happens if it doesn't. Imagine if the resistance is larger, now the car will slow down. Okay? If the driving force is larger, now the car will speed up. If none of them happen and it keeps on moving, that means these two are exactly the same. Now, what is the resultant force? Resultant force is zero. And what happens to the movement? It's going at a constant velocity. So look at the law again. An object will remain at rest, like the first car, or continue to move at a constant velocity along a straight line, like the second car, if the resultant force on it is zero. That is Newton's first law. Maybe send me letter Y if you understand it for yes, Newton's first law. Many people just memorize it without fully understanding the concept, guys, but here it is. Yeah? Thank you, Dinara. Hello. All right. Okay. That is Newton's first law. Newton's second law. Newton's second law says the acceleration of a body is directly proportional to the resultant force on it and takes place in the same direction. Now, simply say you have an object of mass m and the force is F. The acceleration is A. Now, F is proportional to A. F is equal to ma, which is the formula we used earlier, right? Now, that's F here is the resultant force. If I produce a graph of F against A, because F is equal to ma is y equals mx, the gradient is the mass. However, if you switch them around, say A here and F there, the gradient is the reciprocal of the mass, 1 over n. Don't worry too much about the mathematics of it. Just memorize it for now. Mukesh, we are supposed to finish at 7, but I could not do the triple only bit. I'm thinking of just extending it a little bit, probably another, I don't know, half an hour-ish. I'm okay to do that. But if you are triple, you could stay. Right. No problem. Right. I usually have lessons until like Saturday and Sunday. I usually have lessons until quite late. But today my next lesson is at 7:30, so I'm okay. Yeah. Right. That's that. Okay. Second law done. Newton's third law says that every action has an equal and opposite reaction. Or if body A exerts a force on body B, then body B exerts an equal and opposite force on body A. There you go. I have a slide for that, but I think there's probably and copyright issue if I show it here on YouTube, so can't do that. So have a look. So every action has an equal and opposite reaction, or if body A exerts a force on body B exerts a force on body A. That's what it is, right? Right. I think that's pretty much it for those who are doing combined science, guys, right? So forces, scalars, vectors, we did resultant force work, all that stuff, elasticity, Newton's laws we just did and did some questions. VT graphs we did, SWAT we did, equations of motion, stopping distance we didn't do one today, but that one, momentum we didn't do a question on that, and wave stuff we did some of these things, magnetism, permanent induced magnets, magnetic field patterns we did, electromagnetics we did, Fleming's left hand we did, motor we did, Efficos BI also we did. Right, guys, I think that's quite sufficient because I took almost the 2 hours or maybe 6-7 minutes shy of that. This one, right? We shall for the waves required practical. The thing, I think the best way to do this is to use a video on this one, the ripple tank one, because I cannot really get some of the images that I have on this one because of the copyright thing, right? But if you have a question about that, you can ask me. It's a slightly long one as well, right? I'd rather do some questions on these things, which I made for the triple students. So guys, if you are combined science, I think that's pretty much it for you guys. And now we are going to go to triple content. And well, good luck for any of you are doing that exam stuff, right? Good luck for anyone for your exam tomorrow. Right, now let's move to some triple content. The generator effect and EM induction. Now guys, the whole idea behind this is, right, the whole idea behind this is, if you think about a coil, and let's say you connect a milliammeter, or like there's something called center zero galvanometer or a milliammeter. So basically that's a zero at the center. If the current is 1 amp to that side, it will go that way. If the current is 1 amp to the other side, it will go to the other one. So basically you have the 1, 2, 3, 1, 2, 3 like that. Now, if I just leave it like that, well, there'll be no reading, obviously, because there's no power supplies in it, right? Now, if I bring a magnetic north pole fast, like you just move it towards this, there will be a momentarily there will be a deflection. So the pointer will go like that. Why? Because the magnetic field lines from this exert a force on the electrons in the coil, and if there's a complete circuit, it will make them move. However, if you just, let's say you just put just lodge it here and then stop, say you put the magnet here and just not move it, this will remain at zero again. Now, if you take it out, north pole out, it will go to the other side. So if I move in and then out, and if I just repeat it, it will keep on going to left and right, left and right. So the electrons are being pushed one way and the other, one way and the other. That's basically like very much like an alternating current. Now, this idea is basically what we refer to as electromagnetic induction. Thumbs up if you understand the concept of EM induction, what it is. Yeah. There is a right-hand rule, but you don't have that in the spec. That can be used to identify the direction too. Yeah. So that's about the thing, right? So that is what EM induction is. So in simple words, if there is a changing magnetic field through a wire, it will create an electromotive force, EMF. And that's what you refer to as EM induction, which can be shown if you move a magnet or you can keep the magnet still and move the coil. Either way, if there is a relative motion, it will register a small EMF. Yeah, that is the idea. All right. Now, a simple idea about this alternator and dynamo. Now, these are both generators. Alternator creates an alternating current, as the word implies. And the dynamo produces a direct current, because D for direct, you can just memorize it like that. Yeah? Give me some emoji if you understand alternator versus dynamo, the difference. Alternator and dynamo. Alternator is, they're both generators. Alternator produces alternating current, whereas dynamo produces direct current. Right. Now, here we have, in the alternator, here we have a magnetic north pole. And then here we have a magnetic south pole. And then you have magnetic field lines, obviously, from there to there. And now, this is connected to the outside circuit. Now, one of them is connected to one ring, and the other one goes through this without touching the first one and is connected to another ring. And you need to now rotate it. Now, look, this is the exact opposite of a DC motor. In the motor, we give electricity and motion is what we get, right? That's what we give a motor for, right? Imagine you have a motor of a fan. So what do? We give electricity and the motion is what we need. Now, a generator works the exact opposite way. So we move it. Now, let's say we have a handle here, and I can rotate the handle doing that. When I rotate it, what happens now? The coil rotates, and if you connect this to an outside supply, you will actually get an alternate current coming out from that. Right? So what is a dynamo? The dynamo is very similar to this. Oh, by the way, guys, these are called slip rings. Yes, Prashini, yeah, your name is definitely, I remember your name. Yeah. Slip ring, right? These are called slip rings. Why slip rings? Because they kind of, they just go through that and they just slips, right? All the time. Now, yeah, no problem. Yeah, that's good. It's good happy to help. Now, look. Now, people discovered this, invented the alternator, and they were getting this alternating current, and they were like, is there a way to get direct current from this one by doing a small tweak? Well, they did. You know what they did? Here, they had the same thing, exactly the same thing, but instead of having a slip ring, you just put a split ring like the previous one. So you connect a split ring. Now what happens? So you have, like, let's say the you can't see that. Let me just put it here. Let's say now the voltage changes just like that, but when it is about to go to the negative side, the two terminals flip, because that's what happens in the slip ring. I explained earlier in the DC motor what will happen. It will go the same way. Again, it flips and flips and flips and flips and flips, making direct current. This is AC, that is DC. That is the alternator and dynamo situation, guys. How is that? If you have any questions, you can ask me now. Any questions, doubts, anything to do with this alternator versus dynamo situation? Right? Good. Let's go to some questions, shall we? Fine. Here's a question about EM induction mainly, guys. I'm just going to yeah, I mean, the straight line of the dynamo, really, Vishal, is just to say that it is constant. But if I just think about a single coil, it's just going to have a variation. But still, it will all remain on the positive side. So it's technically, it is positive. It is a DC. But there's a variation. DC in one direction, but there's a variation. Yeah. Right. I'm just going to give, oh, not that one, guys. I'm just going to give you 2 minutes as usual, and we'll check the answers in a bit. Let's do this. Any particular triple only theory parts you need help on, you can let me know and I will talk this through. Let's do this question. Any particular bits in space, Mukesh? Anything in particular? About 1 minute left, guys. Yeah, the life cycle of a star. Actually, I have a question on it at the end. So, Mukesh, I will definitely talk you through that. Yeah. Life cycle of a star. I know what you're asking about the nebula and all that, right? Protostar. I'll explain. I will explain. 20 seconds. Right. A magnet is pushed into a coil connected to a sensitive ammeter. I already explained this situation earlier. State what is observed on the ammeter and explain why this happens using the concept of changing magnetic field. So let's say what we can tell for A. The ammeter will deflect momentarily and returns to zero. Yeah, it will not remain like that. It will just deflect and comes back. Explain why this is happening using the concept of changing magnetic field. So as the magnet moves, it changes the magnetic flux linkage really, but GCSE flux is fine. Flux through the coil and exerts a force on electrons, charge carriers. Yeah, that's why there's an EMF. Now, sensitive ammeter. So ammeter has very low resistance, so there's a complete circuit. If there's a complete circuit, there will be a current. Yes, I'm going to go until 7:30, Prashini. Yeah, 7:30. I'm just going to go. I was meant to finish at 7 o'clock, but I'm just doing. Couldn't finish everything in that time. So, yeah. Next one. That'll be current. State and explain 3 ways to increase the size of the induced potential difference. Right. Send me the answer, guys. What would you do? How would you increase the induced PD? Gone? Send me. How would you increase the induced PD? There are a few things, guys. Such a popular question. This one. I just need to see. Increase the not really, Vishal. There is no external current here, right? You have a magnet and you have movement. There's no external power supply, no battery. More magnetic material. How about use a strong magnet? Use a stronger magnet. Yeah, you can get away with what you just. Yeah. There you go, Vishal. Thank you. Use a stronger magnet is one. Thank you. What else, guys? 3 ways. Another one. So we are just pushing it. Use more turns on coil. Yes. Use a coil with more turns in a given length. This is the best way to say this. Because rather than having like a coil like that, we need a coil like this, like really, 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 really close. Yeah. Use a soft iron core. You could do that, but there's another easy one you can do. How about move the magnet faster? Hello? You understand? You can move the magnet faster. A solenoid is the same as a coil, Prashini, right? It is the same thing. So moving the magnet faster. So rather than moving it slowly, just move it like really fast. So if you move it faster, it cuts through it faster and it creates a greater EMF. So 3, use a stronger magnet, use a coil with more turns in a given length, per unit length, whatever, per meter, move the magnet faster. Right? Yeah, we can't really say with this, because in terms of guessing, Mukesh, it's quite difficult to guess like what would come up in these things because there's only one physics paper too, and whatever you get there is what you get there. So like in maths, for example, I did like predicted papers, and my predicted paper 3, there's a short, like a YouTube short I've done to compare them. 12 questions came up in the real paper because we've seen like what came in paper 1, and then we saw what came in paper 2. Now we know from the big pool, I can eliminate that, and then I can kind of, decide what would come up. But that is very difficult to do with these kind of, it's not difficult even, it's kind of very almost impossible to do because there's only one paper and then you get whatever you get. Yeah, that sort of a thing. But a more useful way to think about it is the things on the board here. I've kind of extracted them. These are like most common exam questions. This is what they're based on. So if you weren't here before, guys, just take a screenshot. Yeah. They're very likely questions, guys. So it's a very difficult thing to say. Yeah. Right. Let's see. For the required practicals, Mukesh, probably the best way to do this is because there's a lot of like it's either the practicals done. There are some videos on the YouTube where the practicals is actually done. It's about 6-7 minutes. If you just put the practical and put AQA GCSE, or you just put like AQA GCSE Physics required practicals, and you can get that. That's probably the most effective way. Yeah. The magnet is held stationary inside the coil. State what the ammeter readings and explain why. So ammeter reads 0. Ammeter reads 0 as there is no change in the magnetic field, magnetic flux. So what we need is a changing magnetic flux or flux linkage, you really call it. You need to have a change, which is why when you move it, it works. If you move it faster, you get even higher. But if it is not moving, you're not going to get it, right? Sorry, done. Right. Let's do a question on transformers. Step up, step down. Very, very popular question again. Right? Let's have a look at this one, guys. You got about 10 more minutes left, so we'll do we can do now. So I'll give you about, oh, that's the wrong one. About 2 minutes, guys. Let's do this question on transformers. Let's do it. Transformers. Okay. Helen, yes, my name is Madhu Shank, actually. I have a quite long name. It's a Sri Lankan name, so yeah. About 1 minute, guys, and then we'll check. 1 minute. Okay. A step up transformer has 200 turns in the primary coil, so that is NP, and 3000 coils in the secondary coil, NS. The input voltage V primary is this. Calculate the output voltage. Now, N primary divided by N secondary is V primary divided by V secondary. N primary is 200 divided by N secondary is 3000. Okay. Is equal to V primary 230, V secondary, we don't know. That is the question, guys. What do I do? Simply 200 goes into 3015 times, move the 15 to that side, move Vs to this side. Okay, that's really easy. Vs is equal to 230 multiplied by 15 gives you 3450 volts, guys. Thumbs up if you got this one, or send me letter Y if you got that. Part A, yeah, 3450. First one. Good. The input current is 12 amps, so that's I primary. Calculate the output current IS. Okay, assuming it is 100% efficient. Now, guys, in this question, I'm giving you it's 100% efficient. Some questions ask you, calculate it, state any assumptions you make. So, what do you say? The transform is 100% efficient. Now, remember the power input. Remember, P is equal to IV, right? I primary, V primary is I secondary, V secondary. So, what's I primary? 12. V primary 230. I secondary is what I'm trying to find. V secondary we just calculated as 3450. So what do we need to do? Move it to that side. 12 times 230 divided by 3450. Mm, you get 0.8 amps. That is the right answer, guys. Part B. Part C. Explain why the national grid transmits electricity at very high voltage and low current rather than low voltage and high current. Uh, is this one given? I can check, Vishal. Um, Here are the formulae that you guys need. So VP, yeah, that's given. That's given as well. Yeah. So the ones that are marked with green are given. This stuff you need to know. Yeah. So in the national grid, um, we have the power station. Then we use a step up transformer. And the pylons are here. This voltage is very high, like 400,000. Why? Here's the thing. Remember, power is I squared R, right? Remember P equals I squared R, the other formula for this? P is equal to I squared R. If the current is high, the power dissipation will be very high, meaning this will give a lot of heat if the current was high. That's not really good for us, right? Because we produce all this energy and now it's going to get, dissipate to the environment along the way. That's not good. So we need to keep it minimum. So what do we do? Because power equals IV, if I increase the voltage really high, what will happen to the current? That will be less. Now, that's because the power is constant. Imagine this, P is equal to IV. Let's say if the power is 1000 and voltage is 200, now the current is 5. Yeah, 200 times 5. Now, if I increase the voltage to 1000, oh, the current will only be 1 now. Why? Because you need to have the product to be that. If I increase the voltage to 2000, the current will only be half, 0.5 amps. So can you see, the higher the voltage, the lower the current. So in the national grid, we use very high voltage to keep the current very low so that power dissipation is really low. Right? Guys, the answer to that one is a slightly long one, but fortunately, I have this on my channel where I have actually done my, let me just quickly get that one. I'm getting it really quickly, guys. On electricity, I have a playlist on my channel, and there's a question. National grid, there you go. I'm going to give you the link to this in the chat, guys. So please, yeah, I'm about to finish. I'm finishing the lesson at 1:30 as 7:30 as well, actually, because I have a lesson as well. I have an A-level lesson in a bit. So this is the same question. The national grid uses very high voltages. Explain why using a high voltage is more efficient. So here's the full answer. Sorry about the resolution is not the best, but here's the answer. Let me just show you this. Yeah. Here. Using a high voltage reduces the current in the transmission cables, for one point. Lower current means less energy is lost as heat due to resistance in wires, because P equals I squared R. This makes the transmission of electricity more efficient. Transformers are used to increase the voltage before transmission and decrease it before use. So you increase it first, like in the yellow bit here is a step up transformer, and at the end use a step down transformer to bring it back down to a safe level of 230 in the UK. That is the idea. So that is that question, guys. part C is exactly the same question. So I think that's pretty much it, guys. We did it almost for just under 2.5 hours, and everything we did so far are relevant to you. Good luck for everything. Good luck for your exam tomorrow. If there is anything, you guys can probably message me, or you can put a comment. I'll be checking it again later because I'll be doing a lesson here. So if you put a comment in the thing, if you have a question, I'll be able to answer. Good luck, everybody. That's it for today. Bye. You're welcome.